Okay, so now I'm going to move on, and we're going to talk about some ways that we might describe the actual losses of energy that go on inside this ductwork. So, for instance, this little section that's in the that's actually in the manual, right? Chapter 5 of the Industrial Ventilation Workbook Manual. Okay, at standard temperature pressure, losses are routinely expressed in the following format. Well, what is that? Remember, we're interested in maintaining static pressure. So we're measuring the losses of static pressure, very important to us. And that's equal to, what's it equal to? It's equal to the velocity pressure, right? Remember that like if we have a long duct, right, and we have a certain loss that's giving us because of friction in that ductwork, well, the faster the air is moving through there, the higher the velocity pressure, the greater that loss is because it's more friction, right? You can imagine if it's kind of like dragging something faster, I guess, right? Well, maybe not. That would be, I don't want to go there. So, at any rate, static pressure loss is equal to something to do with the velocity of the air moving through there. In other words, the velocity pressure times some factor we're going to call K, K loss. That's a number that we're going to use, right? That's going to be a factor. That factor may be 0.1, 0.05, depending the smaller the less friction there is, and the less loss there is, the smaller this number is going to be. The greater it is, the larger that number is going to be. And that's going to be, I'm going to rewrite that, is equal to K loss times the velocity pressure. Okay, and that K is going to be different for different circumstances. For a filter, for galvanized ductwork, for plastic ductwork, for dirty ductwork, old ductwork. It's going to be a different number. Okay, so now the thing about velocity pressure is maybe we don't know the velocity, but we do know the velocity at the average velocity air moving through the ductwork. Another way to express it would be K loss times, instead of velocity pressure, the velocity over 4005 squared, right? We just took what we did before and substituted it for the velocity pressure, right? So we can calculate what our static pressure loss is if we know the velocity pressure or if we know the velocity, either way, right? So once we know either one of these two things, and we know what our K is, and we're going to find our K by looking it up in tables. That's not something that we're going to have to calculate. Okay, we're going to find our K by examining tables that'll tell us what it is for elbows and bends and transitions and so on and so forth. Right? So, but all we need to know is either the velocity pressure or the velocity, either one of them, since they're kind of interchangeable anyway based on the formulas that we were using before. Okay, so I'm going to move on to maybe start to apply some of this stuff. Okay, so let's take a look at what we have here. Here is an elbow. The elbow was one of the things we were saying that was really a significant factor in losing some of that potential energy that we call static energy. No question so far, right? Let me just take a quick look. Okay, that's an important element in losing that energy. I'm going to make that a little bit bigger so you can see it a little bit better. Okay, now there's a way that we describe these devices. An elbow. The way that we describe an elbow is we describe it by comparing the diameter of the, remember usually this is a circular duct, the diameter of the ductwork, whatever that happens to be, right? And the radius of the curve. You can imagine a tight curve is going to lose more energy than a gradual curve. And a larger duct is going to lose less energy than a narrow duct because the air has to move faster through that. Right? So the important thing here is that the energy loss that we're going to experience is going to be related to both the diameter of the duct and the radius of the curve. Well, we're going to use a measure for round ductwork that we're going to call R over D. And believe me, you can actually measure, you can actually buy ductwork based on defining it by that number. I'm going to see if I can't make this blow up a little bit. Maybe better to do it this way. Okay, good. I can actually get this even bigger. Okay, so here is various sized, here's galvanized ductwork, okay, and we defined the ductwork by the relationship between the radius and the diameter. Okay, radius same as the diameter, that we call that R over D of 1.0. 2 times the diameter, it's 2.0, and so on and so forth. And for all of these different size comparisons of radius of the turn to the diameter of the ductwork, we then can look up a K value, that value of the amount of loss that we're going to get from that transition. This is a transition, it's changing the direction of flow. Okay, we can look at that. Well, in one case, you can have a smooth transition, which is a ductwork, which is a gradual bend like this. Or more commonly, because it's easier to manufacture, you may have a curve that's made up of different sections. Now, you've gone to the hardware store, Home Depot, and so on and so forth, and you've seen these pieces of ductwork where the turns or the changes in direction are built up from several pieces of ductwork that are welded or crimped together. For instance, you might have a three-piece duct that makes a 90-degree turn. You might have just simple mitered duct, which is just like one piece of duct welded into another piece of duct with no curve. And you can imagine that this one has great losses. And then as it gets closer and closer and closer to a smooth finish, 4-piece, 5-piece, to a smooth finish, it's a smooth continuous duct, you would expect less and less losses. Well, let's take a look at this. For something that's a very tight curve, an R to D ratio of 0.5, right? Very tight curve. If it's just a right angle, well, gee, that K is very large. And then as it comes closer to a smooth transition, it becomes lower. Similarly, as the turn becomes more gradual, as R over D is larger, also the K value comes down. This is the number, this K value is the number that we would multiply the velocity pressure by to figure out how much static pressure loss in inches of water that we would have. The velocity pressure would be in inches of water. K is unitless. The density factor we would only use if it's not standard temperature and pressure. And we would be able to calculate our static pressure loss. So we don't have to do anything exotic. We just have to go to a chart to look this up to calculate that static pressure loss. And if you have several elbows, here, like in that first design, we had 3 elbows, one turned up, one turned across, one turned back down for the filter, going into the filter. Then we'd have 3, each one of those turns would produce a loss like that. Okay, that's how we'd calculate that. So we're slowly starting to build our tools for being able to design this kind of system. Now, what do we know so far? Well, now we're starting to understand how to measure static pressure, what the influences are from static pressure, where we lose static pressure so that we have to account for it when we size a fan or size the ductwork and so on and so forth. So one place we lose static pressure is in the elbows. So we're starting to learn how to account for that. We know where to find this table. This is chart number 13 in the back of your textbook. So next, let's take a look at some other exercises here. Okay, let's see. Well, actually, let me work through this. Okay, K elbow. But what is the actual loss of air flowing through a 60-degree 3-piece? Oh, something happened here, right? I'm glad we did this because they threw a curve in here. And I mean literally a curve. 60-degree 3-piece elbow at this velocity, right? And we could have done it meters per second if we want to do that. R over D is 1.25. Well, I know that the K value, the constant for the loss for a 90-degree elbow, an elbow is typically 90 degree, right? For a 90-degree 3-piece elbow, let's see, 90-degree 3-piece elbow with a R to D ratio of 1.25. 1.25, I don't have that. It's somewhere between these two. Well, the first thing I have to do is, since this chart for a 3-piece 90-degree turn, this chart doesn't have a value for an round a radius to diameter turn of 1.25. So I have to interpolate it's between these two numbers. So between 0.34 and 0.42, the average of those two is 0.38, 0.38. So the first thing that I had to do a real life problem was deal with the fact that I don't know what this is, right? That's the first thing I had to do. And look it up, 3p's, and this is what it's going to be, 0.38. So the next thing I need, let's see, I need to know, let's see, what's my, hang on, I got more of a problem here. It's not a 90 degree, it's a 60 degree. If you've gone through the PowerPoint that Jeff Burton has, do you remember what he's told you to do? If you, whoops, let me quit this. Whoops. Oh. If you remember what he told you to do, if it wasn't a 90 degree angle, if it was a 45 or 30 or something like that, in order to use this table. Anybody get to that or get a chance to go through that? Basically, what he told you to do is that this chart is for 90 degree turns. We don't have a chart for 60 degree turns. So what you should do is you should use the percentage of a 90 degree turn that this is, like 60 over 90. It's 2/3 of a 90 degree turn. So you should multiply this by 0.66. Okay, if I multiply by 0.66, we go down here, multiply by 0.66 times, what was it again? 0.38. It's going to be equal to 0.25. So my K factor is going to be equal to 0.25. I had to make two accommodations there. One accommodation was for the fact that the radius to the diameter of the duct was 1.25, and we didn't have that exact number, so I had to interpolate between those two. And the second accommodation I had to make was say, well, it's only 66% of the losses because it's not a 90 degree turn, it's only a 60 degree turn. So my K factor for a 60 degree turn is 0.25. So now what's my velocity pressure? Well, my velocity is equal to 3440 feet per minute. Okay, so now I'm not interested in my velocity. I'm interested in my velocity pressure. Okay, so what's my velocity pressure equal to? Let me go back here, 2 spots. Well, my 3 spots. My velocity pressure is going to be equal to my velocity over 4,005 for American units, for US units, velocity over 4,005 squared. Well, which was derived from just V is equal to 4,005 times square root of velocity pressure. Okay, so we're just using that formula, that same formula in a slightly different form. Okay, so my velocity pressure is going to be 3440 over 4,005 squared, right? My V over 4,005 squared. Okay, so let's calculate what that is. Okay, 3,400 divided by 4,005. I'm sorry, I made a mistake there, didn't I? 3,440. 3,440 divided by 4,005 equals times itself. How can I do that? First, I'll put this in the memory in case I lose it. Times itself is 0.74. Okay, hopefully I did that right. So this is equal to 0.74. So my static pressure loss in the inches of water, remember if I use all the rights, this is feet per minute, 4,005, this is all meant to be used with velocity in feet per minute. with and so on and so forth, and the losses and the velocity pressure and the static pressure are going to be in inches of water, right? That's all built into that 4005. So that's going to be equal to, it's going to be equal to 0.25 times 0.74 is going to be times 0.25 equals 0.18. I'm going to round it off to 2 decimal places because obviously this isn't the most precise inches of water. Our static pressure loss through that turn is going to, given that velocity that the air is moving through that ductwork with that ratio of diameter to radius, our static pressure is going to be 0.1 inches of water. That's what we lose through that transition that we have to make sure we make up for when we design the ductwork. So I'm going to take a quick look at the chats part down here. Did I miss something? What is that point times 2? Did I miss times 2? Where was that? I see a comment times 2. Oh, okay, never mind. Does that make sense to you guys? Have I lost you, or does this make some kind of sense? Okay, good. So we're not lost yet, right? Think this is not brain surgery. Remember, this has to be something that people that do this kind of work understand and can work with. That's why so much of it bypasses very complicated fluid mechanics and a lot of very difficult math and so on and so forth, and relies on tables and simple formulas and so on and so forth to do these calculations, because real people have to be able to make these determinations. Doesn't have to be perfect, right? But you have to be able to rely on your design to deliver the product that you want, the business end of this thing, what happens at that hood. So you usually build in a little bit of a leeway here for yourself as well. But these things will give you at least a decent shot at a proper design right off the bat. Okay, and you're going to find that we're going to be using a lot of these tables, and we're going to be looking at a lot of different transitions and devices and parts and hoods and so on and so forth. And we're going to have the benefit of technical information from, say, the manufacturer of the hood, from the ACGIH, that describes what you need to make this hood perform to do what you want it to do. We're going to get that information from them. Okay, so I'm going to move on. Okay, let's take a look at this next one. Now let's take a look at this. What is the frictional loss for a length of galvanized iron ductwork with the following parameters? The diameter is equal to 8 inches. The quantity of air that's moving through here is 1,000 cubic feet per minute. The length of the ductwork is 43 feet. Now, it's galvanized iron duct. Most ductwork is galvanized iron. It's a very common material for it. It's a relatively smooth material. At standard temperature and pressure, and R, which is a factor that represents the roughness of the ductwork, is equal to 1. That's no accident. The R factor is based on how rough it is compared to standard galvanized ductwork. So standard galvanized ductwork is defined as having an R of 1. Okay, so now if you use a different kind of material, you would use a different R. If it's rougher, it might be a higher number. If it's smoother, it might be a lower number, and so on and so forth. Okay, and here's some description of what these various factors, what these various numbers stand. The VP, as usual, velocity, pressure, inches of water, or millimeters of water if you're using international units. L is the length of the ductwork. So our frictional loss in a length of ductwork, right? We learned about elbows. Let's learn now about how much we lose to the ductwork that's connected to that elbow, going into that elbow, coming out of that elbow. In this case, we have 43 feet of ductwork. We want to know how much we lose from one end of it to the other end of it, given that air is going through this 8-inch round duct at 1,000 cubic feet per minute. Okay, so now how do we figure that? Well, we use a formula. K times the velocity pressure, just as we did before. Nothing's changed. Same thing as we did for the elbow, right? Velocity pressure times that factor K, which is specific to either the transition or, in this case, the ductwork that we're working with, times the length. Actually, what we wind up with here is we wind up with the frictional loss per foot of ductwork. So then we multiply by the length of ductwork, 43 feet. Okay, now R is going to be 1, so we're not going to, and we're going to work for the most part usually standard temperature and pressure, so we don't need a density correction factor, right? So these two things stay 1 and they actually drop out. We don't work with them. Only difference in measuring the frictional loss, static pressure loss due to a length of ductwork is that we're going to figure it out as inches per inches of water loss, inches of static pressure loss per foot, and then multiply by the number of feet. So that's really the only difference. Well, how are we going to do that? Well, again, we're going to rely on a table for figuring out what our frictional loss in that length of ductwork is. First of all, what do I need? What's here that I know I'm going to need? Let's see. I know, let's see, the formula here is going to be the static pressure loss is going to be equal to K times V, the velocity pressure, times the length. I know the length is 43 feet, and that's in the right units already, so we're all set there. K is unitless, but we got to look that up. That's going to come from a table or something like that. But I need to know what the velocity pressure is. Do I know what the velocity is? Well, no, I don't know the velocity. I know it's 1,000 cubic feet per minute, right? That's the quantity of air. That's Q. So now in order to calculate velocity pressure, I need to know what V is. So I know that Q is equal to V times the cross-sectional area, right? So the velocity is equal to Q over the cross-sectional area. Okay, so what's that going to be equal to? Q is 1,000 feet cubed per minute, and over the cross-sectional area. Well, it's 8-inch diameter duct. This duct has a diameter of 8 inches. So that means it has a radius of 4 inches. I need this cross-sectional area. What units do I need it in? I need it in square feet, right? I'm working with feet, cube feet, and so on and so forth. I need this area. So 4 inches is the same thing as 1/3 of a foot. Everybody agree with that? 4 over 12 is 1/3 of a foot, right? So that's 1/3 of a foot. And the cross-sectional area is equal to pi times r squared. By the way, incidentally, pi. Anybody know what the digits are for pi? 3.141595, I think it's 953, whatever the other two digits are. See what's happening here? Right, Pi Day. This year, this is a once-in-a-lifetime event. I want you to know this. This year, we will be on March 14th, 2015, at 9, I'm guessing at this, I don't remember these other digits, at 9:53 in the morning and 19 seconds, we will have a day and time representing the 2, 4, 6, 8 first 10 digits of the decimals after for pi. Okay, cool, right? This happens once every 100 years, so enjoy it. It's going to be this March 14th. But let me go back to what we're talking about. So now, it's so easy to distract me. So at any rate, so now we need pi r squared. So it's 3.14, close enough for us, times the radius squared. In feet, not in inches, in feet. So that's 1 over 9. 1 squared over 3 squared is 1 over 9. So basically it's 3.14 over 9. So the area, cross-sectional area, is 3.14 divided by 9. Okay, if I'm making a mistake here, just throw a comment in there and I'll go back. It's easy for me to make mistakes when I am doing this quickly. Divided by 9. Okay, that is 0.35 square feet. Okay, 0.35 feet squared. That's our cross-sectional area. So our velocity is equal to 1,000 cubic feet per minute divided by 0.35 feet squared, right? Feet squared into feet, it's going to be feet per minute. It's going to be velocity. That part's going to looks like it's going to work. So I'm going to take my 1,000 divide it by let's see, divide it by 0.35, and it comes out to be 2860. I'm going to call it. I'm going to round it off to 2860 equals 2,860 feet per minute. That is my velocity. I don't need velocity. I need velocity pressure. So now what do I have to do? I have to say my velocity pressure is equal to, it's equal to 2,860 over 4,005. Tedious, right? But not difficult, just a little tedious. Squared, right? Again, standard temperature and pressure, so I don't need that density correction factor. Okay, and what is that going to be equal to? Well, that's going to be equal to, let's go back here and do this again, 2,860 over 4,005 equals 0.71 times itself. I'll just put that in there in case I lose it, is 0.51. Our velocity pressure is equal to 0.51 inches, 0.51 inches of water. Okay, so now I got what I need for my formula. I'm missing one more thing though. This velocity pressure is equal to 0.51 inches of water. My length is 43 feet. I'm missing my K. Well, I wonder if I have a place I can look that up, like a table. Well, in fact, we have what's called a nomograph. I like nomographs. Nomographs are fun. Okay, and that nomograph is, let's see, elbow, branch entry. Let me see if I can't find the right one. No, that's branch entry. How about this one? Here we go. Okay, chart 5. Chart 5 is an interesting chart. We have what's called a nomograph. Nomograph is a series of scales that are either adjacent or separated, and that you can use to calculate various things. For instance, right here, even before I do anything else, we could calculate the cross-sectional area of a circular duct by knowing its diameter. Let's see if we got it right before. 8-inch duct has a cross-sectional area of roughly 0.35 cubic feet. We could have just used this chart to figure that out. Okay, and look, we have a volume flow rate. What was a volume flow rate? Well, you want to know something. 1,000 cubic feet per minute. Well, if we send 1,000 cubic feet per minute through an 8-inch duct, which has that cross-sectional area, let me connect those two numbers. I happen to go up. I happen to have a thing over here where I can put a line. I'm going to choose line, and I can tell it that I want just a plain line. Okay, so I'm going to connect 8-inch duct with 1,000 cubic feet per minute airflow. Well, what's that going to do for me? What that's going to do for me, actually, I'll even go past here. 1,000. Okay, what does that do for me? Well, let me put another line here. Line, good. Going to get another line, except this one I'm going to put a little arrow on. Okay, and the place where it crosses this line right here, that point over there, that's my duct frictional loss. So if I have 1,000 cubic feet per minute of air flowing through a duct, and that duct is 8 inches, the K value is, I kind of made it a fat line, right? I'm going to call it 0.03 for argument's sake, because it's going to be difficult for me to do anything closer. 0.03, did I say 0.03? Yeah, 0.03. The frictional loss is 0.03 per foot. So our static pressure loss is going to be equal to, kind of a cool, I really could have avoided calculating the velocity because by using this formula, it actually gives me the K value. Well, I need the velocity pressure anyway, don't I? So I would have needed to do it, but I have a trick on that too. Okay, so what's it going to be equal to? It's going to be equal to 0.03 times 0.51 times 43. Okay, our static pressure loss is going to be 0.65 inches of water. That's how much static pressure that we're going to lose by sending air at 2,860 feet per minute through a 12-inch round duct. That's the amount of static pressure that we're going to lose. I'm going to call it 0.066. Okay, and just write it in here. So our static pressure loss is equal to 0.66 inches of water. Okay, let me look back and see how you guys are doing. You guys okay over there? How about that? Did I lose you yet? Are you guys off? Did I not? Okay. It's a little tedious, isn't it? You got to kind of go step by step, but look at the tools they give you. Look at we're basically standing on the shoulders of giants. They've given us a whole series of tools that we can use to understand how to calculate these various materials. We've only used, I think if I go back, I'm not going to go all the way back to that page. We've only used basically about 4 or 5 formulas. And everything else we've done has depended on the use of a chart or a table or something like that. And they're relatively simple formulas, no calculus or anything like that. It's easy to get confused, but as long as you stick with your units, you make sure the units are what's intended for you to use, it should work out pretty well. Just wanted to point out to you that 8-inch duct, 1,000 cubic feet per minute, means that you have a velocity of approximately 2,800 feet per minute and a static pressure of roughly half an inch of water. This table just gave us all 4 numbers that we were calculating before. I, in fact, probably didn't have to do most of what I did. I got from this one table by connecting the duct diameter and the number of cubic feet of air per minute that we're moving, the Q. It gave me my K value, my velocity pressure, right? And my velocity and my velocity pressure. It gave me basically everything that I needed to solve this formula, K times velocity pressure times length. All were obtainable from that one table. Okay? All right, good. So that's cool, right? I mean, that really is cool. Okay, so now I find it cool anyway. I mean, I have odd taste, but that's one of the reasons why I like this particular topic, because you can really do amazing things with this. Okay, so now just to end the night, okay, we're going to take a look now at another thing that can go on here is we can have a single duct and a single fan supplying several hoods. So another kind of transition that has a loss of static pressure is called a branch. And we're going to take a look at how we're going to solve this for a branch. Okay, how much static pressure loss takes place at a branch? And I probably would have put this off and done some other stuff first, but this is the sequence that they covered in the industrial ventilation workbook. So let's stick with what Jeff is doing here and continue with the sequence of work that he's doing. What's the estimated static pressure loss in inches of water, as we are wont to do, for a branch entry of 30 degrees where the branch entry velocity is 4,500 feet per minute. V is 4,500 feet per minute. Okay, and to say CGIH method is exactly what we've been doing. Okay, here's our formulas down here again. We know what the velocity is, so we can calculate the velocity pressure. The static pressure loss is equal to K times the velocity pressure. What's the velocity pressure equal to? It's equal to the velocity, 4,500 feet per minute over 4,005 squared. Okay, good. Let's calculate that. That's equal to this, and I'm going to multiply it by itself. That's equal to 1.26 inches, right? Velocity, pressure, inches of water. That's 1.26, right? What's K equal to? K is specific to this kind of transition. So I need a table that'll help me out with that specific transition. Well, sure enough, we got a table. I've got to turn that off. And here's our table from the textbook. Come on. There we go. Okay, here's our table. I'll try and enlarge it. Okay, so now what do we know about this table? Okay, there's the thing that we're most interested in this table is the angle at which this intersects this this transition. Now notice that these two ducts are both delivering air here. Air is going in, it's traveling this way, air is traveling this way, and it's combined here. So they have to expand into a larger duct. It would be very inefficient to try and put a T in here. I have a big duct and put a T in. We know that that's enormous frictional loss involved there. Really make if you can imagine, imagine this as a traffic pattern, and cars merging into a larger highway or something like that. If they came in at a right angle, it'd be a real mess, right? We want it to merge in as efficiently as possible. So this angle is important to us. The closer this angle is to zero, the less frictional, the less conflict we have with the mainstream of air. The bigger angle that goes in here, the more frictional losses we're going to have that lose static pressure for us. So this angle, and I believe that they told us that the angle on this particular problem is a branch entry of 30 degrees. Okay, well, let's see. 30 degrees, here's 30 degrees, and our loss fraction, in other words, our K, for this transition is going to be equal to 0.18, right? So we just simply use this table for this branch entry transition. Okay, and did I say 0.08? I forget what I said. Come on, open up for me again. I said 0.18. You guys probably told me that, right? Let me see. Nope, you didn't help me. Okay. I'm putting you to sleep by this time, right? It's been a while. Okay, so this is going to be equal to 0.18. 0.18. So our static pressure loss is going to be equal to 0.18 times our velocity pressure in inches of water, 1.26. So it's going to be equal to, let's see, 1.26 times 0.18. That's going to be equal to about 0.23 inches of static pressure loss. 2-3 inches of water. That's our loss of static pressure when we have that kind of transition. Okay, and I think that pretty much covers the calculations that were in the text. Now, a couple of comments. Comment number one, I'm going to put together an exercise to be due next week. It's going to be the simple calculations based on what we did tonight and what we did last week, kind of as a homework assignment. Maybe I'll give you a little extra time, but I want to prep you, get you guys starting to exercise yourselves besides reading the chapters and so on and so forth. You want to make sure that you're actually trying some of these things and that I know you're keeping up. The object of this exercise is to give you guys a chance to try this stuff, to make sure that you understand it, and give you an opportunity to get it all right. I'll give you an opportunity to submit it more than once, so you have every possibility of getting a 10 on the exercise or assignment or homework or whatever you want to call it, so that it's good for your grade and it's good for you in general because it'll help prep you for when you finally have to take an exam on this. Not good to look at me doing all this little cumulatively simple things and then all of a sudden get hit with something complicated on an exam. Much easier to learn it in these little steps. And I want to make sure you guys are keeping up with that. The other thing I wanted to mention, remember in the lab, we're going to try some of this hands-on. It's going to be very exciting. Well, I'm going to spend maybe about 20, 30 minutes doing it. I don't want to kill too much time, but I want you to actually see this in operation and measure static pressure in a duct. Okay, so now the other thing I wanted to mention is that for those of you that haven't had a chance yet, in your material for your industrial ventilation workbook, the material came with your industrial ventilation workbook, was an industrial ventilation workbook, and tonight we covered chapter 5 in that book, industrial and indoor air quality workbook, which we'll be using in the last third of the semester or so. You also got a CD. On that CD is a bunch of PowerPoint presentations by Jeff Burton, and you'll also see some spreadsheets produced by Jeff Burton. Those spreadsheets are auto-calculating spreadsheets. We're going to take a look at them in just a second. Okay, I'm gonna just want to play one of these right now. Turn the sound up.
We're going to be covering chapter 5 in the industrial ventilation workbook. Incidentally, if you look at chart number 2, you will see the local exhaust ventilation system has 5. Also remember, we need to always provide replacement air as part of our problem.
See, so what I was driving at here and showing you that, hopefully you were able to hear that. Were you able to hear the audio that went along with each one of those PowerPoint slides? There's audio embedded in them. Yeah, so you have an expert in this field. He's retired at this stage. He's, I believe, in Arizona. He's retired, but he's basically the guy. He's the head of the. He runs for the last 10 years. I think he's run the ACGIH committee on industrial ventilation. So you have a lecture from a real expert in this field that's available to you. You hear his voice. He shows you his slide, shows you his, tells you about his experiences and so on and so forth. So these are really valuable. And you have one of these slideshows for each one of the chapters. So I really encourage you to go back and listen to the slideshows for the previous chapters, and particularly for this week's chapter, because we're really now getting into the design of these things. Okay. And that's on your CD. That's part of the material that comes with this course. And when we cover next week, I'm not sure, maybe it's chapter 6, maybe it's not. I'm not sure. I'll have to take a look at the syllabus. But when we cover the material next week, a great preparation would be to watch that slideshow, and it'll probably take you a half hour, an hour, or something like that, right? To watch that slideshow before class, before you come to class, because you'll already come in there prepared to understand the material that we take from that point. Okay, so the other thing I wanted to show you is one of his spreadsheets. If I can't find it here we go. Spreadsheets, industrial ventilation spreadsheets, U.S. units, chapter spreadsheets. Here we go. It's chapter 5. So this spreadsheet is the calculations that are associated with the chapter that we just worked on. And you'll notice, I'm going to blow this up. You'll notice that they're set up so that there's a yellow and orange cells here. So in these yellow and orange cells, the way that you would use this spreadsheet is the yellow cells represent an input, something that number you could put in. The orange represents the output or the results of the calculation. For instance, this formula right here, equation 24, this is a solution on a spreadsheet for the static pressure loss in a duct fitting, K times VP times the density correction factor. So I'm going to change this to density correction factor. I have to, before let me do this, I think I have to say save as, save a copy of it to my desktop. I'm not sure if yours is the same way. And I may have to turn off the protection. Yep. In order to turn off the protection, I have to go into Tools, Protection, Unprotect Sheet, and type in Jeff, Jeff. Whoops. lowercase, JEFF. Okay, and that'll turn it off. I think that you'll have notes in your, you'll have a note along with your CD that explains this. It's on your CD, a little text file that comes with this. I'm going to change the density correction factor to a 1 because usually that's where we're dealing with standard temperature and pressure. So if our K value, as it was in some of the problems, was something like 0.28, and our velocity pressure was 1.2, it would calculate our static pressure loss for us. We would be able to do this calculation, have this actually do the calculation for us. Here's another one. This one is static pressure loss that we calculated before, a length, the R versus D ratio from your for your turn elbow, so on and so forth. I'll go back over that next week maybe. There's a lot of these that we haven't covered yet, so I'm not going to get too involved in this. However, you get the idea here. These are calculations that are involved in, I guess this was chapter 5 through 7 or something like that. So there's other calculations here other than the ones that we've done so far. But you can use these spreadsheets to accelerate your learning of how to do these calculations and accelerate the actual calculations themselves. Right? So we could do this calculation much quicker. I think next week would be a better time to maybe, since we're coming to the end of this, might be a better time to really go into this in more detail. And we'll go over all of the ones up to this point. Next week, if we can get to it, we'll go over all the ones that are from the previous chapters 3. We're skipping 4 for now. We're going to come back to that. So we'll go over the spreadsheets for 3 and 5 and 6 next week. And we'll introduce those and we'll understand how we might use those particular spreadsheets and the automated calculations that they have in them to do some of our calculations. Okay, so are there any questions? Right, you have a lot of great tools in this package, and like I said, don't be surprised if by the end of the semester you don't really feel that you feel confident enough to actually go out and design and evaluate these kinds of systems. Because by the end of the semester, you are going to have the level of knowledge about how these things are designed that you're going to be able to make real judgments with this stuff. So, you guys okay? Still there? All right. So keep in mind, next week, we're going to spend maybe 20, 30 minutes in the lab and maybe stay there if it's comfortable to continue with the lecture. But we're gonna set up some ductwork. If you get there a little early, you can help me out with it. That's C014 in the basement. And we'll actually do some static pressure measurements on some ductwork. Those of you that have taken the environmental lab, especially the 4-hour version of it, may have done all of this stuff before, and that may have quite a bit of experience and have done more than we're going to do in that short period of time. But at least we'll start to understand a little bit better how these static pressure measurements work and why they're so important to us. So have a good night.